Hey everyone, welcome to our channel. Today we are diving to something super cool. How digital signal processing can make your voice sound crystal clear. Ever been on a call where echoes and weird sound delays make it impossible to understand the other person? Yeah, we all have been there. But don't worry. In this project we are tackling that problem head on with echo cancellation, pitch conversion, and a bunch of other audio tricks using signals, networks and systems. This is our mini project where I, Bhavik Desai, Tanish Chavan, and Rahul Chaturvedi will be presenting something very crystal and clear about signal processing, which will help in echo cancellations and voice enhancement. Whether it's for telecommunications, smart assistants, or assistive devices, this system is designed to clean up your voice, making every conversion smooth and clear. So stick around because in the next few minutes we will be breaking into all down from how echoes work to how we cancel them out and showing you the magic behind the scenes. So all right, let's jump in. Coming on to our next slide is the acknowledgement that we would like to give to our professors who guided us throughout the way. We sincerely express the gratitude to Professor Najib Gatte and Professor Shanti Swami for their invaluable guidance, support, and feedback throughout this project. We also thank the Electronics and Telecommunication Department at Sardar Patel Institute of Technology for providing the necessary resources. Special thanks to our family, friends, and everyone who contributed directly or indirectly to the successful completion of our project on human voice enhancement. Moving on is the introduction. Human voice enhancement is the process of improving the quality, clarity, and the intelligibility of speech by reducing noise, echo, and other distortions. You must all know about this. This technology plays a crucial role in various applications such as telecommunication, hearing aids, voice assistant, and public address system. The goal of this project, the crystal goal of this project is to design and implement algorithms that filter unwanted noise while preserving the natural characteristic of speech, thereby ensuring improved user experience and communication efficiency. What is this project about? Now I would like Rahul Chaturvedi to continue with the same.
Hello everyone. Today I'll be talking about an exciting project my team has been working on. The focus of our project is to improve the clarity and quality of recorded human voices using digital signal processing techniques. Our system applies advanced techniques like echo production, echo cancellation, and pitch conversion to ensure that the voice not only sounds uh, clearer but also retains its natural essence, whether it's for phone calls, assistive devices, or voice recognition systems. The goal is to provide smooth, high-quality voice transmission, making communication better in everyday life. So, what exactly is an echo? Echo is the sound you hear when your voice reflects off a surface, like a ceiling or wall, and it returns to your ears with a slight delay. Imagine shouting in an empty hall and hearing your voice bounce back a second later. In telecommunication settings, this can be problematic because the repeated sounds overlaps with the original one, causing confusion and reducing the clarity of speech. For example, during phone or video calls, these echoes create a frustrating experience, forcing the listener to strain harder and understand the conversation. Echo cancellation comes in as a solution to this problem. It's an essential process, especially in applications like conference calls or hands-free communication, where external noise and reflections can disrupt the flow of conversation. Using sophisticated algorithms, an echo canceller identifies the delayed or reflected sounds. It then estimates the echo pattern and subtracts it from the incoming audio signal. This way, only the original voice is transmitted, ensuring crystal clear communication without distracting repetitions. Our project has real-life applications in a variety of areas, such as telecommunications, assistive listening devices, voice recognition systems, and many more. Ultimately, our system ensures that whether you're on a call, using a smart assistant, or speaking through a hearing aid, your voice remains clear and easy to understand. Over to Tanishk now.
So now I would like to move upon high pitch and low pitch sounds. So what exactly are high pitch sounds? So High-pitched sounds are basically sound having higher frequencies. They often feel sharp. Imagine a whistle or a child's voice. High-pitched sounds aren't just about being loud. They are crucial in enhancing speech clarity, especially in noisy environments. Imagine you are at a bustling coffee shop trying to hear someone. If they speak in a higher pitch, their voice stands out against the background noise, making it easier to understand. This quality of high-pitched sounds is super valuable for telecommunication systems and voice recognition technology, where clarity is the key. Many of these systems adjust pitch higher to the frequencies to improve intelligibility. Now we move on to the low pitch or the low frequency sounds. Just like high pitch sounds are high frequency sounds, the low pitch sounds are low frequency sounds, producing deep, rich tones. Think of sound of a bass guitar or a deep male voice. So lower pitch sounds are often associated with authority and depth, which is why broadcasters and public speakers often use them. A lower tone can make the listener feel more engaged and gives the speaker a sense of presence. Now we would like to move upon the practical applications. The practical applications include echo cancellation include the clear audio in telecommunication systems, video calls, and conference meetings by removing the delayed sound reflections. It also improves the sound quality in hearing aids and prevents feedback in public address systems, ensuring smooth communication in large spaces. Now moving on to the practical applications of high pitch and low pitch sounds. High pitch speech enhances intelligibility in telecommunication systems and voice assistants, while low pitch adds authority in broadcasting and public speaking. Pitch adjustments also aid in speech therapy and enrich sound quality in music production, making communication and audio more effective and engaging. Now, we would like to show you the implementation of the project we have created.
Let's come on to the implementation now. So let's go through each line of the code to understand what it's doing. It's a very simple code. It uses deconvolution and convolution, which is taught in signals and systems using fast Fourier transform and Laplace transform. Here we will be using Fourier transform because here we are analyzing the thing instead of designing it. So for coming on to the first line, y comma fs is equal to audio read ref dot wave. Here audio read loads the audio data from the file ref.wave, which is the audio file that I recorded in the .wav extension. Y stores the audio signal data as a vector or a matrix if stereo. And fs is the sample rate in hertz of the audio, which defines how many samples per second. So how many samples are generated on the basis of which the quality of the sound that will be presented when we are presenting the output will be shown. Now coming on to the next step, that is calculating the length and the duration of the audio signal. Y length calculates the total number of samples that can be seen. Secondly, T calculates the total duration of the signal in seconds by dividing the sample count by the length by Fs. So what we can see that T is equal to Y length by Fs. So total time duration is calculated using that. Then the third point is that time is a vector from 0 to Y divided by Fs, creating the time axis in seconds. So the graph plotting can be made easier. Third is the third part, that is the most important part, is the impulse response matrices. So matrix, if U input 1, U input 2 and U input 3 represents an impulse response for different echo effects, for generating a strong echo effect, weak echo effect and a medium echo effect, and thereby the respective sample rates are given. Then applying the simple for loop for k equal to 1 to 3. So each for loop is run 3 times. So 3 iterations are generated. Initializing the impulse response filter. So T is a zero initialized vector, the same length as an audio signal Y, which will store the impulse responses. Now coming on to the selection of the ecosystem based on the iteration. So on the basis of which the predefined loop helps us to, in order to understand the displayed message and the echo level strength that has been applied. Then coming on to the next part is placing the impulses in T based on delay and amplitude. So for I equal to 1 is to size means the iterations will be run on the basis of the size of the input 1 samples that are being generated. And the time can be calculated using the round function, which helps us in rounding of the figure, and thereby is equal to U input I comma 2. It iterates over the selected matrix U input and converts the delay in the seconds to samples and sets the amplitude U new input I comma 2 at that exact position in t. Now coming on to the part where the major implications are there, where is the plotting of the input impulse response and the output. So first creating a figure and having a subplot function, plot x label, y label and the title with the grid on. Then coming on to the performing the convolution in which the major applications are being applied. So how is this convolution making the echo is what we are going to learn through this small short of code, small block of code. So out length is equal to y length plus length of y plus length of t. So here we are determining the total length minus 1. As we had learned in the first session of Najib sir, that when we are taking the total, when we are using convolution function on MATLAB, it gives us random graphs because the sampling that we have been doing is half of it. So in order to take the total samples, it should be the total length minus 1 so that all the samples have been counted. Now performing the Fourier transform of out length and then multiplying it by the other Fourier transform of the other function. Thereby convolution can be expressed as a multiplication of the Fourier transforms. Is that because of the property of convolution, that is property of convolution using Fourier transform, which says that the Fourier transform of one function into Fourier transform of other function gives us the convoluted function. And thereby proceeding further, we can normalize the echo signal and thereby give us the by dividing it by the maximum absolute value. Similarly, plotting the impulse train using the same methods using subplot, x label, y label, and title. Coming on to the performing the deconvolution to remove the echo. Now echo has been generated. Now I want to eliminate that echo. So the only way to eliminate it is using inverse fast Fourier transform. So just performing the inverse fast Fourier transform and then again normalizing it so that we obtain the normalized deconvoluted signal with no echo generations, and thereby this can be also plotted using the same methods of subplot, x label, y label, title, grid on, etc. Moving further is the how to play that audio, which you will be hearing in a couple of minutes. Now coming on to the part that is the actual implementation of playing the encode and decode signals. So you for your doing this, we need one particular function, that is the sound function. Now, if we are doing this in MATLAB, but however, if we were doing in Python, then PyTorch library will be used, in which the audio py.sound or library is also there, which is used for the same function. Coming back to the topic, sound function is used to play these echo signals and thereby it plays out the y out and the xx, the deconvolute signal and the echo signal with pauses for duration of our original audio. Now coming on to the next topic of playing low pitch and high pitch echo signals.
Alright everyone, let me walk you through the section of the code where we modify the pitch of the echoed audio by adjusting the playback speed. First, let's talk about the lower pitch section. Here, we reduce the sampling rate by dividing it by 1.5. A lower sampling rate means that the fewer samples are being played per second, which slows down the playback. As a result, the sound becomes deeper, giving us a lower pitch. Next, we use the sound function to play the echoed signal Y out, but now with a reduced sampling rate. This slower playback is what creates the low pitch version of our audio. We also print a message on the console to let our user know that the low pitch echoed signal is being currently played. Now, since the playback is slower, we need to adjust the pause duration. We multiply the original time t by 1.5 to ensure the playback finishes before moving on to the next section of our code. Now, let's move on to the higher pitch section. In this case, we increase the sampling rate by multiplying it by 1.5. The higher sampling rate means more samples are being played per second, which speeds up the playback. The faster the playback, the higher is the pitch of the audio. Again, we use the sound function to play the echo signal, but this time with a faster speed, giving us the higher pitch version. We again display a message on the console to inform the user. Since the playback is faster, we at this point we reduce the pause duration by dividing the original time t by 1.5. This makes sure that we do not have any unnecessary delays before continuing on to the next part of the program. So to summarize, by changing the sampling rates, we can modify the pitch of the audio. Slowing down the playback lowers the pitch, while speeding it up raises the pitch. We also need to adjust the pause durations accordingly to match these changes in the playback speed.
So now moving upon the actual implementation part, it is the part you are all excited for. It is what exactly will we get as the output. So now I would like to run the code. So I'd run the code by pressing on the run button, and now we'd first have a signal which is echoed.
Hello, 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 hello. My name is Bhavik this side. Hello, 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 hello. Hello, 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 hello. My name is Bhavik this side. This is noise cancellation rule. This is noise cancellation audio.
So now since we had the echoed signal, now we would like to listen to the normal sound which will be played now.
Hello, 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 hello. My name is Bhavik this side. Hello, 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 hello. Hello, 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 hello. My name is Bhavik this side. This is noise cancellation video. This is noise cancellation audio.
So now since this part is done, now we would like to show the low pitch frequency or the low pitch sound.
My name is Bobby. This is my name is Bobby. This is enhancing installation. This is enhancing installation.
Pretty funny, right? Now let's move on to the high pitch audio.
Hello, 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 my name is Bobby Krishnan. Hello, 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 my name is Bobby Krishnan. This is noise cancellation room. This is noise cancellation audio.
So yeah, this was the implementation of the signals. So now I would like to move upon to explain you about the graphs. So the green graph you can see on the top of your screen is the input graph. The input graph is basically the rev.wav file that we imported from the MATLAB cloud, which we exported to the MATLAB cloud. The red graph you can see is the impulse train. It is the natural response of the system. Now to obtain the output signal with echo, we have to perform the Fourier transform of the input function along with performing the Fourier transform of impulse train and multiplying the two signals. We get the convoluted signal, which is the output signal with echo, which you can see with the blue graph shown below. Along with it, to get the signal after deconvolution, we need to use the inverse Fourier transform on the output signal with echo. Also, to normalize the signals, we have divided it with the sampling frequency or the sampling rate. Now, the signal after deconvolution is similar to that of the input signal, but it is smaller in length, which also shows that it has reduced the unwanted noise present in the system. Uh, you everyone for your patient hearing. If you like the video, consider to drop a like, share this video, and subscribe if you want to get more content related to signals and systems. Thank you.